Okay, good afternoon, everyone. Welcome back. I hope that you had a fantastic long weekend and you took a break from everything and had some fun. We're moving on today, and this is lesson 31.12, where we are doing something called logarithmic differentiation. And once this lesson is done, we will be done with differentiation. So after today, what we're going to be looking at is the opposite of differentiation, which is called integration or anti-differentiation. Logarithmic differentiation isn't what you might think it is. It isn't that we're differentiating logarithmic expressions, although that's part of it. Logarithmic differentiation is a technique of differentiation that's used in two very, very specific situations. In one of these situations, using this technique of logarithmic differentiation is a requirement. There is no other way that you can do it. In the other of these two situations, logarithmic differentiation is used to make our jobs a lot easier. You could certainly differentiate some of these expressions we're going to be seeing in the second category without using logarithmic differentiation, but your life becomes so much simpler if you use this technique that we're going to learn today. So here's the first situation. When you have a function that's going to be differentiated and there's no differentiation rule, you have to use logarithmic differentiation. So a classic example would be something like x raised to the sine of x. There is no rule that we have learned, nor does there exist a rule for finding a derivative of a variable raised to a variable. So we have a rule for differentiating a function where there is a variable in the base and a constant in the exponent, like y equals x squared. We know how to differentiate that. We have another rule that you just learned recently for differentiating something where you have a constant in the base and a variable in the exponent. For example, y equals 2 raised to the x is something that's differentiable at this level. You know how to differentiate it. There's a rule. But when it comes to something like y equals x raised to the sine of x, you have a variable in the base and you have a variable in the exponent, and you do not have a rule for that. There's no rule that exists. No. The second situation where it isn't a requirement that you use logarithmic differentiation, it's just that it would be a really, really smart move to use logarithmic differentiation, is if the rules would combine in such a complicated manner that your life would become excruciatingly difficult in differentiating it. So for example, consider that function y equals that expression raised to the 5. I'm not going to attempt to read it, but if I differentiated that, I would have to wrap the 5 down in front of the base, which would stay the same. Then I would drop one from the exponent, and then where the real trouble would begin is I would have to multiply by the derivative of that thing inside, which would involve the quotient rule. And when I found the derivative of the top as part of the quotient rule, I would have to use the product rule. And when I found the derivative of the bottom as part of the quotient rule, I would have to use the product rule within the product rule. And it's going to become very, very messy. The likelihood that I could differentiate it with respect to x using all of those rules and not make a mistake is very, very low. It's going to be easy to make a mistake because there's too much going on. So although we do have rules for differentiating such a function, that process would involve way too much, and we just don't have time for that. So what are the basic steps in using logarithmic differentiation? Well, the first thing that you do is you take the logarithm of both sides. We prefer, as you've discovered in Math 31, to always take the natural logarithm when we're dealing with logs. Then we're going to differentiate implicitly and solve for the derivative. In this particular problem, we have to find dy dx, where y is equal to sine raised to the x of x. What that means is that y is equal to the sine of x raised to the x. So how is logarithmic differentiation going to deal with this? So the first step is to take the natural logarithm of both sides. We have the ln of y equals the ln of sine of x raised to the x. I can rewrite this now as the natural logarithm of y equals x times the natural logarithm of the sine of x, because the logarithm of a power is equal to the exponent times the logarithm of the base. I'm allowed to move that exponent down in front. Now what I've set myself up for is success, because I can use the product rule on the right-hand side and implicit differentiation on the left-hand side. The derivative of ln of y is 1 over y dy dx. So now I'm going to use the product rule. The derivative of the first, which is x, is 1, multiplied by the second, which is the ln of the sine of x, plus the first, which is x, times the derivative of the second. So what is the derivative of the natural logarithm of a thing? It's 1 over that thing multiplied by the derivative of that thing. Now we have 1 over y multiplied by dy dx is equal to the natural logarithm of the sine of x plus x. And I don't think we really have to write cosine of x over sine of x. We can write cotangent of x to make our lives just a little bit easier. And for the most part, everybody, we're pretty much done. Dy dx is now equal to, when I multiply both sides by y multiplied by the natural logarithm of the sine of x plus x cotangent x. Now y was equal to sine to the x of x, so if you want, and you don't have to, but if you want, you could say dy dx equals, we have y, which is sine to the x of x, multiplied by the natural logarithm of the sine of x, plus x times the cotangent of x, and we are done. That's the derivative of sine to the x of x. Let's take a look at the second example. Find dy dx if y equals the cube root of x sine x over x squared minus 1. You know, I guess if you wanted to, you could use the power rule combined with the product and the quotient rules to differentiate this. But let me show you how using logarithmic differentiation will make our lives easier. We're going to have the natural logarithm of y equals the natural logarithm of x sine x over x squared minus 1 raised to the 1/3. Now, what we can do with the right-hand side is move that exponent in front. So now we have the natural logarithm of y equals 1/3 times the natural logarithm of x sine x over x squared minus 1. And my preference here is to move that third to the other side. Let me show you why that's the case. What I'm about to do is rewrite this natural logarithm of all this stuff in the argument as the natural logarithm of x plus the natural logarithm of sine of x minus the natural logarithm of x squared minus 1. I'm using my product and quotient rules for the logarithm. The logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. And the logarithm of a product is the sum of the logs. So the natural logarithm of AB equals the natural logarithm of A plus the natural logarithm of B. The natural logarithm of C over D equals the natural logarithm of C minus the natural logarithm of D. So what I'm doing is I'm using the product and quotient rules for logarithms to rewrite that single logarithm as 3 separate logarithms. Now, I do have a coefficient of 1/3 in front. Rather than multiplying that third into each of these, I'm just going to write 3 ln y. I'm going to multiply both sides by 3. That way I don't have to deal with that fraction everywhere. Now I differentiate everything. the derivative of 3 ln y is 3 times 1 over y times the derivative of y, which is dy dx, equals 1 over x plus the derivative of ln of sine is 1 over sine multiplied by the derivative of sine, which is cosine, and then minus the derivative of ln of x squared minus 1 is 1 over x squared minus 1 times the derivative of x squared minus 1, which is 2x. And you know what? I mean, we're pretty much done. Just rearrange for dy dx. dy dx is equal to 1/3 y. So now I'm bringing that 3 back to the other side where it becomes a third. I'm also multiplying by y, and then times 1 over x, and then plus, well, cosine over sine is cotangent. Let's just write cotangent. And then minus 2x over x squared minus 1. And incidentally, I don't think with any of these problems that we're working on with logarithmic differentiation, I don't think you want to simplify this. You don't want to find a common denominator and put this all together. The reason we did this technique was so we could avoid all of the algebra. Typically speaking, this technique of integration is used in problems like this because you just want to get an expression that you can use to find the slope of a tangent. Whether you put in for y the cube root of x sine x over x squared minus 1 is entirely up to you. I would say, though, it's not necessary because if you want to find the value of dy dx when x is 5, for example, you'd put 5 everywhere up here for x, and you would put 5 in here for x, and then put the result for this y value up in to your derivative. So I don't think it's necessary to do the substitution. In other words, everybody, that's the answer. 1/3 y multiplied by 1 over x plus cotan of x minus 2x over x squared minus 1. So that's it for the lesson. On page 395, there's a set of 3 problems that you can be working on. Some of these will be finding derivatives of expressions that you have no rule for. Others will be finding derivatives of expressions that you have a set of rules for, but if you use this technique of logarithmic differentiation, your job just becomes so much simpler. I hope that lesson made sense. Have a great rest of the day, and we will talk to you soon. Take care.